Okay, Math 1100, final exam review for derivatives. In question 1 here, we have the product of two expressions. We could think about each expression as different functions. It's the product of two functions, f and g. The product rule is f prime g plus g prime f. So following the product rule, y prime equals the derivative of this expression, which is 4x times g, x squared plus 4, plus g prime, which is the derivative of that expression, 2x times f, 2x squared plus 1. Simplify, 4x to the third plus 16x plus 4x to the third plus 2x gives us 8x to the third plus 18x. Okay, similar thing here on question 2. We want to find f prime, which is the derivative, and we've got the product of two functions. But on question 2, the second function here has an inside function and an outside function, so it's going to require a chain rule. So if we say f and g for our two functions, then using the same product rule as before, we could say f prime of x equals the derivative of this, which is 2x times g plus g prime, which is 3 times 2x plus 2 squared multiplied by the derivative of the inside function, 2 multiplied by f, which is x squared plus 3. Okay. So we have 2x times 2x plus 2 to the third power plus, if we combine some like terms here, we're going to have 6 times x squared plus 3 times 2x plus 2 squared. Now, if we compare this side to this side, both sides have a 2x squared, or a 2x plus 2 squared in common that can be factored out, and 2 as a common factor that can be factored out. So I'm going to factor out a 2 and a 2x plus 2 squared. That's going to leave x and 2x plus 2 left over from that side. And from this side, we're going to have a 3 and an x squared. It's supposed to be squared right there. X squared plus 3. Now, cleaning this up a little bit inside of there, this becomes 2x squared plus 2x plus 3x squared plus 9. So that's going to be 5x squared plus 2x plus 9. So that's 5x squared plus 2x plus 9 So for final answer, we have 2 times 2x plus 2 squared times 5x squared plus 2x plus 9. Okay, question 3. Supposed to find the third derivative. So we have to start with the first derivative, f prime of x. That's going to be negative 8x to the third plus 6x squared minus 2. F double prime is negative 24x squared plus 12x. And then the third derivative is negative 48x plus 12. Okay, on question 4, this is going to require implicit differentiation with a product rule here and there in this, because we're taking the derivative with respect to x, but sometimes we're taking the derivative here of y. Anytime you take the derivative of another variable with respect to x, you have to use the chain rule. So looking at this first term here, x y squared, since it's x times y squared, it's a product rule. So if we consider one of the functions as f and the other function is g, so f and g, then following the chain rule is going to be f prime, which is 1, times g plus g prime, which is 2y dy dx. So this is g prime times f. Okay. Now we can take the derivative of this 4x squared y. That's going to be another chain rule. So we can consider another f function here and a g function there. So f prime is going to be 8x, so f prime g plus g prime, the derivative of y is 1 dy dx. So that's g prime times f. Okay. And then another product rule here, because we have 3x squared times y squared. So if we have another f and g, f prime becomes 6x, so f prime g plus g prime, which is 2y dy dx, g prime times f equals the derivative of negative 1, which is 0. So we have the whole thing there. Any term that has a dy dx I'm going to keep on the left side. So this term, for example, is 2xy dy dx plus this term 4x squared dy dx plus this term, which is 6x squared y dy dx. Any term that doesn't have a dy dx is going to get subtracted over to the other side. So we're going to have a negative y squared. From there, we're going to have a negative 8xy from there, and a negative 6x y squared from there. Now every term on the left side has a dy dx, so that can be factored out, leaving 2xy plus 4x squared plus 6 x squared y equals negative y squared minus 8 xy minus 6x y squared. And we can divide by this term on the right side there to get dy dx by itself. So dy dx equals, this term here is the numerator, negative y squared minus 8x minus 6xy squared divided by this term there as the denominator, two xy plus 4x squared plus 6x squared y. Okay. Question 5. Open intervals in which the function is increasing or decreasing. This is going to involve the first derivative, finding critical values, putting them on a number line, finding test points to figure out which intervals are positive or negative. So f prime is going to be a quotient rule. So f prime of x equals low d high minus high d low all over low squared. If we simplify this, this part here becomes 2x to the third plus 8x, and this part becomes 2x to the third. So the 2x to the thirds cancel, so we're left with 8x over x squared plus 4 squared. Now critical values can come when the first derivative equals 0 or when the first derivative is undefined. To find out where it's undefined, you're going to want to focus on the denominator to figure out where it's 0. But x squared plus 4, well, x squared is always going to be a positive quantity, and then you're going to add 4 to that positive number, which is still positive, and then you're going to square that positive number. So x squared plus 4 squared is never going to be 0. So we don't get any critical values because f prime is undefined. Now to find out if it's a rational function, to find out where it's equal to 0, you set the numerator equal to 0. So the critical value, if you solve 8x equals 0, the critical value is x equals 0. So placing that on a number line, and then choosing some test points. For example, I could test -1. Here I could test +1. If I plug in a -1, let's plug in a -1 here. Into the numerator, I'm going to get -8, which is a negative number. Now in the denominator, I said it's always going to be positive. Regardless of what you plug in for x, the denominator is always going to come out to be positive. So it's a negative divided by a positive, which makes a negative interval there. Now if I use my test point of +1, 8x is 8, which is a positive number. The denominator still is always positive. Positive divided by a positive is a positive. So this interval here is negative, and this interval here is positive. Negative denotes a decreasing part of the graph. Positive denotes an increasing part of the graph. So you would say decreasing from negative infinity to 0 and increasing from 0 to infinity. Question 6, relative extrema. That phrase means relative minimum, relative maximum, or local minimum and local maximum. That's very similar to question 5. You take the first derivative, set it equal to 0, or find out where it's undefined to find the critical numbers, place them on a number line. So we need to find g prime of x. This is going to be a chain rule because we have an inside function and an outside function there. So the derivative is dropping that exponent down in front, 2 times x squared minus 4, decreasing the power by 1, and then multiplying by the derivative of the inside function, 2x. So g prime of x is going to be 4x times x squared minus 4. X squared minus 4 is the difference of squares. It becomes 4x times x minus 2 times x plus 2. So the critical numbers are x equals 0, x equals 2, and x equals negative 2. So choosing some test points of 1, 3, negative 1, negative 3. Those are going to be my test points. If I plug in my first test point here, negative 3, in for all three factors here, 4 times negative 3 is negative 12, so that's negative. Negative 3 minus 2 is negative 5, so it's negative. And negative 3 plus 2 is negative 1, which is negative. But a negative times a negative is a negative. So negative 3 produces a negative interval. Now if I choose negative 1 as my test point there and test that, 4 times negative 1 is negative. Negative 1 minus 2 is negative, but negative 1 plus 2 is positive, and a negative times a positive is a positive. Now if I test 1 as my test point, 4 times 1 is positive, 1 minus 2 is negative, and 1 plus 2 is positive. Multiplied all together results in a negative. And then testing 3 is a test point. 4 times 3 is positive, 3 minus 2 is positive, and 3 plus 2 is positive, which results in a positive. Now the plus minus plus indicates decreasing and increasing intervals of the function. So if we're taking a look here, the graph is decreasing, then when it gets to negative 2 it starts to increase, so that means that's a local minimum. And then between negative 2 and 0 it's increasing, but then at 0 it decreases. And it decreases from 0 to 2, and then when it gets to 2 it starts to increase again. So we have a minimum, a maximum, and a minimum. So minimum values are when x equals negative 2 and when x equals 2. Maximum, well, before we do the maximum, we need to figure out the y values that go with these. So negative 2 comma what? And positive 2. So to find these, you have to go back to the original function here. Negative 2 squared is 4. 4 minus 4 is 0. And 0 squared is 0. So it's negative 2 comma 0. Same thing with 2 would be 2 comma 0. Those are your minimums. Maximums happen when x is 0. Plug in a 0 into the original function, you get 0 squared, which is 0. 0 minus 4, which is negative 4. Negative 4 squared is 16. So there's your max. 2 local minimums. Question 7, an absolute extrema has to be found a little bit differently. It starts the same way with the first derivative and finding critical values. So f prime is 3x squared minus 6x, and you set it equal to 0, and then you have x equals 0 and x equals 2. Where this problem becomes different, because we're finding absolute extrema, is you don't do a number line like we did here on this problem. You go back to the original function f and test the value of f at your critical numbers and at each endpoint of your closed interval. So we need to find f of -1, f of 0, f of 2, and f of 3. Whichever one of these four values is the smallest is going to be our absolute minimum. Whichever one is the largest is our absolute maximum. Okay, so f of -1, if you plug in a -1 and cube it, you get -1. -1 squared is 1. 1 times -3 is -3. So that makes -4. If you plug in a 0 for both x's, you're going to get 0. If you plug in a 2, you're going to get 8. Minus 2 squared is 4 times 3 is 12. So that makes -4. If you plug in a 3, 3 cubed is 27. 3 squared is 9 times 3 is 27. Now, what this means, if you happen to have two numbers that are the same, or in this case, two pairs of numbers that are the same, the smallest of these two here, they're both absolute minimums. So, absolute minimum is -1, comma, -4, and also 2, comma, -4. The absolute maximums are 0, 0, and 3, 0. Okay, next question 8. Concave up or concave down is the second derivative. Now just a suggestion here on question 8, just looking at it how it's originally written, we've got x times 6 minus x squared, so not only is it a product, but part of the product is going to be a chain rule. I would suggest that you multiply this all together. It might make it easier to find first and second derivatives. So 6 minus x to the second power is 36 minus 12x plus x squared. So we get x to the third minus 12x squared plus 36x. Now that it's separate terms, it makes finding derivatives easier. F prime is 3x squared minus 24x, which means that the second derivative, f double prime, then equals 6x minus 24. And if you set that equal to 0, we get a value of x equals 4. So much like question 6 or question 5, now that we have that value of 4, we can place it on a real number line, test points on either side, so 3 and 5, go back to the to the second derivative. If I test a 3 right here for x, I get 18 minus 24, which is a negative number. If I test a 5 right here, you get 30 minus 24, which is a positive number. So this indicates a concave down part of the graph, this indicates a concave up part of the graph. So it's concave down from negative infinity to 4, concave up from 4 to infinity. Question 9, find the derivative. So the derivative of exponentials, if we have the derivative with respect to x of e to the u, that equals e to the u du. It's the chain rule. So we find y prime. The 2 is just a coefficient, so that just stays 2. Now it's e to the u times du, so the derivative of this, which is 14x, so simplifying gives us 28x, or sorry, 28x e to the 7x squared minus 2. Question 10, taking the derivative of a logarithm. So the derivative with respect to x of the natural log of u is 1 over u du. But we have a rather complicated expression inside of the natural log. So what would be easiest is to separate this into multiple natural logs or multiple logarithms. So we've got an x to the 5th function and we've got an x plus 3 to the 1/2 function. Since they're being multiplied together, you can separate them into separate logarithms using addition. So it's natural log of x to the 5th plus natural log of x plus 3 to the 1/2. And then bringing the powers down, it's going to be 5 times the natural log of x plus 1/3 times the natural log of x plus 3. Now taking the derivative of the natural log there, derivative of natural log of x is 1 over x. So we got 5 times 1 over x. And then the natural log of x plus 3, the derivative of that is 1 over, so we've got 1/3 times 1 over x plus 3 times the derivative of x plus 3, which is just 1. Now, hold on. I all of a sudden placed a 1/3 in there. I'm not looking at this very carefully. That should be a 1/2. That should be a 1/2. That should be a 1/2 there. Can't read my own handwriting. I apologize. So, simplifying this is 5 over x plus 1 over 2x plus 6. Okay. Similar type situation on question 11. We have the natural log of a quotient here. So we can separate that into multiple logarithms with a subtraction. First thing though, since this 5 is on the outside of the expression, I'm going to move that straight away down in front of the logarithm. So y equals 5, and now I'm going to separate this into multiple logarithms using a subtraction. Natural log of x squared minus 9 minus natural log of x squared. So y equals 5 times the natural log of x squared minus 9 minus 5 times the natural log of x squared. And now we take the derivative of the natural log of x squared minus 9. So we're going to have 5 times 1 over x squared minus 9 times the derivative of x squared minus 9, which is 2x, minus 5 times 1 over x squared times the derivative of x squared, which is 2x. So we're going to have 2x times 5 is 10x over x squared minus 9 minus, now this x can cancel with one of those x's, so 5 times 2 is 10, so 10 over x. And question 12, find the equation of the line tangent to the graph of the function y equals x natural log of x at the point e comma e. So we've got to find y prime. The derivative is a function that can tell us the slope of a tangent line at any given point, and in order to make the equation of a line we have to have a slope. So that means we need the first derivative, and here we've got a point, so we have a point in the slope. So y prime, if we look at this, we've got the product of two functions. One could be f, the one could be g. So f prime is 1, so 1 f prime times g plus g prime times f. So y prime equals natural log of x, x's cancel, plus 1. So there's y prime. To find the slope of the tangent line at the point, we've got to plug in the x value, which is e. So at e comma e, slope plug in an e right here, the natural log of e is 1. 1 plus 1 is 2. So the slope is 2. Now if we want to make the equation of a line, it's y equals mx plus b. The slope goes in place of m. Y is e and x are both e. So we have e equals 2 times e plus b. If you subtract 2e on both sides, you get negative e is equal to b. So the equation is y equals the slope 2x minus e. Okay, question 13. I'm first going to rewrite as x squared plus y squared to a power of 1/2. Now, these two symbols there mean partial derivative. Partial derivative of z with respect to x, partial derivative of z with respect to y. And fxy equals is the same as z equals. So, the first one, with respect to x, we've got a chain rule because we have an inside function and an outside function, so drop the power down in front. Decrease the power by 1, so you have negative 1/2, and then take the derivative of the inside function. Now this is a partial derivative with respect to x, so that means y squared is a constant, like any other number like 10 or 20, whose derivative would be 0, so derivative would just be 2x. So the 1/2 and the 2 cancel, and you get x times x squared plus y squared to the negative 1/2. Now the partial derivative of z with respect to y, same thing, chain rule, we'll drop down the power in front, decrease the power by 1, and then multiply by the inside function. Now we're taking the derivative with respect to y, so x is a constant whose derivative is 0. So you just take the derivative of y squared, which is 2y, and again the 1/2 and the 2 cancel, so we have y times x squared plus y squared to the negative 1/2. Okay, deciding to take it easy here as we near the end of this review, I decided not to put second partial derivatives on the exam. So let me change this simply to first partial derivatives. So there won't be 4 second partial derivatives, there's only going to be first partial derivatives. So the partial derivative with respect to x and the partial derivative, so partial derivative with respect to x and partial derivative with respect to y. So first with respect to x, this is going to be a quotient rule, low d high. Now the derivative of the upper function, or of the numerator, with respect to x means that y squared is a constant whose derivative is 0, so the derivative of the upper portion is 2x minus high d low. Now if we're taking a look at the denominator, 2xy, remember we're taking the partial derivative with respect to x, so y is a constant. Now I'm going to rearrange this and call it 2y times x. So 2y is just a coefficient of x, much like an expression 10x. If we were taking the derivative would just be 10. So if we're taking the derivative with respect to x of 2yx, the derivative is just 2y. All over low squared, which is 4x squared y squared. Now, cleaning this up a little bit, here we're going to have, if we combine that right there, we're going to have 4x squared y, and then combining that, we're going to have minus 2x squared y plus, the reason it's plus is because we have minus and negative there, 2 negative, so plus 2y to the third. Combining like terms gives us 2x squared y plus 2y to the third. So there's a partial derivative of z with respect to x. Now, partial derivative of z with respect to y, same thing as going to be a quotient rule. So we've got low d high. Now up in the numerator with respect to y, x squared is the constant this time, whose derivative is 0. So the derivative is going to be 2y minus high d low. Now if we take a look here, now y is the variable, 2x is the coefficient. So it's 2x times y. So with respect to y, the derivative is just going to be 2x all over low squared, 4x squared y squared. Now if we want to simplify this, x squared y squared, combining some like terms in the numerator, this combines into 4x y squared minus 2x to the third plus 2x y squared. Combining some like terms there. Okay, and I just found a mistake. I apologize. But right there, this is low and that's d high. So d high would have come from here. X squared was a constant whose derivative is 0. I forgot about that minus sign right there. So the derivative should actually be negative 2y. My apologies. Which is going to make that negative 4x y squared. So combining like terms in the numerator there is going to give us a negative 2x y squared minus 2x to the third over 4x squared y squared. Well, before finishing up, just noticed we can actually simplify each one of these a little bit more. They each have a factor of 2 there that could be simplified, and they each have some y's there that can be simplified. So that y cancels, that becomes a 2, that becomes just a y, that becomes a 1, that becomes a 1, and that becomes a 2. So let me clean this up here. We're going to have x squared plus y squared over 2 x squared y. Okay, very similar. They have these 2's that can simplify and a 4, and then they each have some x terms there that can simplify. We're going to have negative y squared minus x squared over 2x y squared.